All right, hello, grade 12s. We are taking a look at the last lesson of the whole entire year, which is regressions of sinusoidal functions, but where you're making your own table of values. Now, most important point is when we're doing our own table of values, we need to include 5 points within the same period. Now, really quick, we talked about this the other day, but we'll talk about it again. Let's say we have a sinusoidal graph. And it's not perfect, but it looks something like this. And I can pick any period I want. So I can pick a minimum to a minimum. I can pick a maximum to a maximum. But the idea is I could pick any period. Now let's deal with this period here. Now, sinusoidal functions exist in a way where that max is going to be exactly the halfway point between the two mins. So if this is a distance of, let's say, 8 apart, then exactly at the halfway point where the distance from the min to the max, or the max back down to the min, each of them will be 4 from the center. Now these are split very equally. This is always true for any sinusoidal function. Now the other thing to kind of consider is that we know that every single sinusoidal function has a midline. And not only are those max and mins important, but those midline points are as well. So the 5 points we want to hit in one period are going to be these 5 points. Now again, I have 2 mins because that's the period I selected. I have min, middle, max, middle, min. But if I had started elsewhere, I could have had max, middle, min, middle, max, etc. So those are the 5 points that I'm looking for. Now this first example is a pendulum on a grandfather clock, and that pendulum swings from left to right. At its minimum height, the bottom of the pendulum is 12 inches from the ground. During its swing, the bottom of the pendulum raises 5 inches from the minimum height, which means it's a maximum of 17 inches from the ground. The time it takes for a pendulum to move back and forth is 4 seconds. At t is equal to 0, the pendulum, as it is at its minimum height, we want to determine a sinusoidal equation that best represents that scenario. Now, what I'd like you to do, because there's a typo here, it says is the pendulum at time 0 is at its minimum height. But in the question, it kind of contradicts itself. It says the pendulum starts at the furthest point to the left. I'd like you to just ax all of that for me. So we're going to go with time is equal to 0, the pendulum is at its minimum height. Okay, now taking a look at this, we should be aware that there are 2 variables here. We've got time in seconds, and we've got height in inches. And I know that at time is equal to 0, the pendulum is at its minimum height, which is 12. Now, when I take a look at a grandfather clock, and this is my pendulum, it is at its minimum height. When it swings this way, it's now at its max. So if I'm graphing that, it looks like this. And then it swings back to the middle, which is its minimum height again. And then it swings this way, and the height goes up, and it swings back to the middle, and the height goes back down. So one full swing back and forth is 4 seconds. That means it went all the way here, etc. Which means that's 2 full periods we're talking about. I'm only interested in 1 full period. So when I take a look at this, my time isn't actually going to be 4 seconds at the very furthest point. It's only going to be 2 seconds. And at 2 seconds, it's going to reach back from its min back down to its min once again. Now at this point, once I know that first point I'm including and the last point I'm including, everything else can be found by talking about averages. So right in the middle of 0 and 2 is the number 1. And right in between 2 mins is a max. So I have a max of 17. Those other 2 points are going to be the midline. Right between a min and its max is its midline. It's exactly halfway through. And right between the min and its max is that mid-height. Now to find that mid-height of that midline, I'm taking the average of my max and my min. Essentially, I'm always finding the average to find a middle of two values. So I can find that average to get 0.5. I can use that average to get the mid height, which is 14.5. And I could do the same thing in that next gap between the max and the min, and I would get 14.5 once again. Now, we talked about this last class and how to get this table of values. We're just finishing off the question. Now, I want to do a sinusoidal regression. And so I'm going to plug in my regression equation into Desmos, and I'm going to get all those A, B, C, and D values. So here we go, 0.5. And I'm going to plug in what I know, making sure to double check. Now, if I go ahead and plug in my own table of values, I really should get a regression of 1, because I'm doing this experimental or calculated data. I'm not actually taking a look at data and tracking it in real time. I'm saying, okay, based on my calculations, this is where I'm expecting it to be. And as we say that, we should be expecting a regression of 1. Not always, but sometimes if you don't have 5 points within the same period, it'll give you some weird graph that doesn't match the points that you're trying to talk about here. And you'll get an R squared value that isn't 1, which is a sign that maybe you need a better table of values, or maybe you plugged something in incorrectly. And when I do that, I can get the values I'm looking for. Of course, I'm always writing down the non-rounded values. In the odd chance that we've gotten something incorrect, then we can always go ahead and have our teacher, when she's going ahead and looking through our work, to make sure we're on the right track. Okay. Hopefully, when you take a look at things like that, you noticed that your R squared value was in fact 1. After making the table of values, everything else stays the same. The one thing I will point out is in my final answer here, I used Y and I used X, but the question does specifically call time T. So to have the most accurate final answer, I really shouldn't use X, because that variable's already been defined. And if I'm going to change the name of one variable, probably going to change the name of both variables. So I'm going to call height H and time T, just so that it matches the information provided to me in that question. From here on out, I want you to pause the video, try the remaining questions, and see what you get. All right. And I'm going to do them now, and we'll see if we get the same thing. So at what height above the ground will the bottom of the pendulum be after 6.5 seconds? I plug in X is equal to 6.5. I find that point of my graph. So X was 6.5 because that's where the T variable is. It's on my independent axis, and I get Y is equal to 14.5. And it says, what is the height above the ground? And that's going to be in inches. The last question says, at what times will the bottom of the pendulum reach a height of 15.25? Y is equal to 15.25 for the first and third time. So the first time is here. So Y is equal to 15.25. The first time is at that 0.597. If I'm rounding, that's 0.60 seconds. And the third time isn't this guy, but it's that guy. And if I'm rounding, I get 2.60 seconds. Okay, that is it. All right, and our next example, we've got Evie and Des jumping on a bed. They're having a sleepover. Evie starts jumping on the bed. Her minimum height is 36 inches above the ground because that's the height of the bed. Her maximum height is 24 inches higher than her minimum height. Yeah, you've heard that right. Evie has a vertical of 2 feet. That's insane. But each full jump takes 1.5 seconds. We want to determine a sinusoidal equation that represents Evie's jumps. So when I take a look at this, I need to make a table of values. Much like the last example, I have time and height. My height is in inches, my time is in seconds. And if you've ever jumped before, we know that when you originate your first jump, you are starting on whatever surface you are starting to jump on. No one starts jump mid-height. So, at time is equal to 0, Evie is at her minimum height, and her minimum height is 36 because that's how tall her bed is off the floor. We also know that her jump ends after 1.5 seconds, which means after 1.5 seconds, she's back and landed on that bed. At the halfway point, so exactly halfway between 0 and 1.5, and again, to find the halfway point, we're simply adding those two numbers together and dividing by 2. So after 0.75 seconds, directly between the two mins, she is at her max, and her max is 24 inches higher than her minimum. So 24 plus the 36 gives me 60. Now, to find the remaining 2 points, we're really just taking a look and getting a whole bunch of averages. So for her time, we need to find the average or the mid time in between 0 and 0.75 seconds, and between 0.75 seconds and 1.5. And again, you do that by getting its average. So you add those values, divide by 2. You add those values and divide by 2. And when you do that, we should get 0.375 seconds for the first time gap and 1.125 seconds for that second time gap. We do the exact same thing between max and min to find the midline. So if I add 36 and 60 and divide by 2, I get 48. And I hit that midline both on the way up and on the way down. Now we have our table of values. And once we have that table of values, we can go ahead and do that sinusoidal regression. Now, notice that I've already typed in the sinusoidal regression equation for the last question. So I'm simply going to delete all of the data from the last example and go ahead and type my new data. That way, my table still says x1 and y1, so the equation for the regression that I've plugged in still works. But I just need to work with the new data. Again, I'm expecting an r² value of 1 because that data was calculated by me. And I calculated it based on the fact that I know sinusoidal curves should follow a certain pattern. And when I go ahead and get that, I get specific A, B, C, and D values. So take a moment, jot all of that down, pause the video if you need time to plug that in yourself. But I do get numbers here. Now, fun little fact, as you're going through this, you might notice that some numbers pop up more than others. Okay, so you may notice that for whatever reason, we happen to see 1.5708 a lot, and we might see 3.14, 159 a lot. Because we're working in radians, a lot of the numbers for the phase shift tend to be some sort of fraction of pi. So 1.5708 shows up a lot because that's exactly half of a pi, like half pi, which is exactly pi over 2, which is kind of interesting to note, but in case you were wondering. All right, and of course, I'm rounding to 2 decimal places in my equation. And I'm getting this as my answer. Again, just like the last question, you could go ahead and use H and T instead of X and Y. Because this question doesn't predefine time as T or height as H, then I am free to use X and Y as I need. The next question says, draw a clearly labeled graph which represents 2 complete jumps for Evie. All right, I want you to pause the video and draw those 2 clearly labeled graph. And when I do that, I'm taking a look, I'm drawing from time of 0 to time of 36. Oh, sorry, not 36, time of 3. Okay. And feel free to use whatever that point is when I've reached another min, because I'm starting at a min, as my scale. Like this time it is exactly a number that we are likely to use, but you truly don't need to pick a number that's like a 1, 2, 3. I'm choosing 1.5 and 3 because those are my mins. Now, here's the beauty of this. I'm going to just ignore my Y scale for a moment. I know this is a min. I know this is a min. I'm going to erase this in a moment. I realize this does not look accurate. However, I know when I graph things, I know the max falls exactly between the 2 mins. So I'm going to make sure that whatever scale I go up by, I don't even have to label it, is that I can indicate what that max value is. And I also like to graph the midlines. Now the midlines exist halfway between each min and max. So when I'm taking a look at things, yes, my scale is going up by 1.5, but I've broken things up in a way that makes a lot of sense for what I'm about to graph. Now, if I'm taking a look at my values from my table of values, the numbers for height that I want to graph are 36, 48, and 60. I recognize those as all multiples of 12. So I'm actually going to go up by 12 because I know that I'm going to hit those values really nicely. So 12, 24, 36, 48, 60. But picking a scale that works best for you and the scenario is truly a great skill to have. Okay, and I'm going to go ahead, I'm going to label things time in seconds. I've got height in inches. I don't actually need this graph anymore now that I've chosen a scale that works for me. And I'm going to say Evie's height as she jumps on the bed. I'm going to draw some grid lines, specifically grid lines for the values that I'm going to use the most. So I'm going to use the min quite a bit. I'm going to use the max a decent amount, and I'm going to use the midline a decent amount. So I'm going to use those as my grid lines. And I'm actually going to go ahead and put grid lines on all these other values because I am going to use them to draw some points. Oh, oops, should have made those a bit longer. There we go. Now, I know my grid lines happened really quickly. I know yours will take a little bit longer to do, and that's totally okay. All right, now here's the beauty of it. I know that my mins exist at 0, 1.5, and 3. That's why I chose to do my scale. I chose my scale accordingly so that I can have the min values, essentially one period from the beginning. And because I've chosen those, I know my maxes happen halfway between. And I know in between my min and max, I'm always going to hit the midline. So notice I didn't actually go ahead and have to follow my graph on Desmos to get those points. Now that I've thought through my scale, I can just fill in those blanks. Now, as a reminder, this shouldn't be like a pointy thing here. It has to be a smooth curve. So I tend to like to start off trying to make that smooth curve as best as I can. And by drawing those additional points, not just the max and the min, it makes it much easier to graph. Because now I have more dots to follow or more points to follow. Now notice I'm not drawing an arrow at the end because it told me to only graph for 2 complete jumps. So I don't need an arrow because I don't actually know if Evie jumps more than that. All I know is that the graph ends after 2 jumps because it's indicated as such. Now the graph also says to be clearly labeled. So to be clearly labeled means I need to label the characteristic points. So the characteristic points are obviously my X and Y intercepts as they exist. I only have a Y intercept here, but also my maxes and my mins. And quite honestly, I can get a good chunk of these from my table of values, as well as I can grab these from Desmos, no problem as well. But if it says clearly labeled, I need to make sure that I have those labels accordingly. All right. And that's my graph. So I have a title, scale, labels, all of the things that make my graph complete. Now, the next question says to indicate Evie's range. So the range is her min to her max. That should be pretty straightforward at this point, where I get 36 as the min, the max of 60. The next question. Determine when Evie will reach a height of 50 inches above the ground for the first time. So height is my Y variable. So I'm going to plug in Y is equal to 50. And specifically, I care about the first time that that happens. I get X is equal to 0.415. Or if I'm rounding to 2 decimals, I get 0.42 seconds. That is the point in time where she reaches that height for the first time. Now here's a fun little question. Des decides to join Evie jumping on the bed. She believes because of the bed, her minimum height will be the same, but that she will jump higher than Evie. How could you change the sinusoidal equation to possibly represent Des's jumps? So, we know that we have Evie, and she's jumping something like this. Okay, it's not a great diagram, but pretty good. Des is going to have that same min because, again, the bed is there. Let me redraw Evie's. Okay, so Des will probably do something like this because she's jumping higher. We don't really know if her jump's going to take more time, right? Because we don't have that information. All we know is that she's going to jump higher. And again, this is not a great diagram, but it's not bad. Now, what can we say about changing that equation to possibly represent Des's jump? Now, first things first, I know a couple of things. My A value represents my amplitude. My amplitude is the distance from my midline to the top or from my midline to the max, or to the bottom, sorry. Now, that's true whether I'm Evie or whether I'm Des. Now, if I am Des and I'm jumping higher, I'm going to have a higher amplitude. So my A value is going to be higher than Evie's. We don't know how much higher she's jumping, so I can't tell you for sure. But if I'm taking a look at the equation and Evie's amplitude is 12, then Des must be 12.1, 13, 15, 16, etc. Okay? The other thing I know from a graph is the D value represents my midline, where my midline's located. Now, as we just drew when we're talking about the amplitude, the midline for Des is somewhere in the middle. The midline for Evie is also somewhere in the middle, but because they both have the same minimum and Des is jumping higher, my midline would also have to be a higher value. So this has to be higher than Evie as well. Now, when we take a look at what we could possibly do, we need to make sure that A and D value that change appropriately, right? Because if my amplitude goes up by 2, then my midline actually has to go up accordingly, right? I need to make sure that we have the same thing. So here, if I had Evie's amplitude of 12, her midline was 48, so that the bottom she would reach is 36. So 48 minus 12 gives me that 36. Whatever I choose for Des as an amplitude, let's say I choose 15, okay? I need to have my midline a particular number so that when I go that number minus 15, I hit 36 as well. So I need to make sure that I have that same minimum if I'm changing the equation. So a possible answer can be like A is 15 and the D value is 51. Again, we are not asked to pick numbers exactly, but we're just asking about how that equation could possibly change. Now, if you were doing a question like this on a provincial exam and you're like, man, I have no clue, okay? Oops. You're welcome to like map out a scenario here, right? I already know my equation for Evie. It's this guy over here. Let's just change some numbers for Des. So I know the min's the same. I know the max would have to be higher, okay? And I don't know, let's say that max, instead of that max being 60, that max is 70. I would also have a new midline, right? The average between 36 and 70. And I could actually use Desmos, to do that math for me. 36 plus 70. I take that answer and divide by 2. And I get the same value. That ends up being 53. So I'm going to plug in 53 here. Notice that when I compare my equation for Evie, the one that we originally had here, to this new equation that would represent a possible equation for Des, I have a different A and a different D value. B and C have actually stayed the same in this case. So something just to be mindful of. But I can kind of play around with it if I don't actually know how the equation would change. I can try things out with a table of values and then actually see how an equation would change. All right, last question. We've got Jamie riding a Ferris wheel for 5 minutes. The diameter of the wheel is 10 meters, and its center is 6 meters above the ground. Each revolution of the wheel takes 2.5 minutes. Okay, let's just kind of map this out here. So, oops, I'll draw a better circle than that. Hold on. Okay, I've got a Ferris wheel. Its center is 6 meters above the ground. So wherever the ground is, I'm imagining it's not touching the ground because I don't want that Ferris wheel to scrape. But that's 6 meters. We also know that the diameter of the wheel is 10. Okay, so that blue is 10. Which actually kind of makes a lot of sense. Because if the diameter is 10, the radius has to be 5. So I can get a lot of information from that. What can I get? I can get that at the lowest point of the Ferris wheel, I'm 1 meter above the ground. Because again, if the distance from the ground to the center is 6, and the radius of the circle is 5, then at the lowest part of the circle, I am at 1, specifically 1 meter. And the highest point of the circle, way up here, I'm not just 10 meters, I'm 11 meters, because I've just found out that I'm at least 1 meter off the ground from where the closest point to the Ferris wheel is. And then the halfway point would be exactly 6, because the middle of the Ferris wheel is 6 meters across from the ground. Now that tells me a lot of information, and a lot of information that I'm about to use for my table of values. We're really loving these time height examples, so we're just going to continue on with it. Now, I don't know about you, but most Ferris wheels that you likely have been on, you don't get on at the top. You don't even get on at the middle. Usually you get on at the bottom. Because it does not specify otherwise, it is safe to assume that when we board that Ferris wheel, we are getting on at the bottom, and that bottom height is 1 meter from the ground. Okay? Now, again, we're starting at our min, which means we're going to go mid, middle, max, middle, min again. And we actually have those numbers. Min, middle, max, middle, min. We just have to figure out the time. Now, in the equation, it says, let's just close this a bit. In the question, it says it takes 2.5 minutes to do a full rotation. So I know that to get from the minimum to the minimum once again, that's going to take 2.5 minutes. And I can use my idea of averaging to get the other points. Can you pause and see if you can figure out the other times in that table of values? Okay, so the first time I'm trying to find is I'm going to try to find the exact middle because that's the easiest average to do. I'm adding 0 and 2.5 and I'm dividing by 2 to get 1.25. And I'm essentially just continuing to average those two numbers to find that middle value over and over again. So to find this middle value, I'm adding those 2 times, 0 and 1.25, dividing by 2, and I get 0.625. And I'm doing the same thing between 1.25 and 2.5, adding them together, dividing by 2, and I get 1.875. All right, you know the drill. Plug that into Desmos, get that regression equation for my sinusoidal graph. And just like last time, I'm not actually going to delete everything. I'm just going to delete my values directly from the table of values and re-input new ones because I find it quite easy to not have to retype in that equation for sine every single time. Oops. Now, if I've done things correctly, I should, again, get an r squared value of 1. I'm looking at my graph, and I should get, I should see that my sinusoidal graph kind of matches exactly how I would have drawn it in if I were to say, draw a sinusoidal curve of best fit. Right? I know where the maxes are. I know where the mins are. I should be following that. Now, if for whatever reason you're going through this and you're like, Miss T, my equation numbers are way off from you, please check that you are in radians and not degrees. If you are in degrees, your numbers for your equation will be off. Obviously, if you did this on a test or a quiz or whatever, you might lose a half mark, but you wouldn't lose all of the follow-through marks. I would just plug in the exact values that you got, and then you could still get everything correct. So just be mindful of that we're in radians. Okay. Before I was talking about that 1.57 coming up a lot. And again, that's just pi over 2. And because we're dealing with radians, it's kind of expected that number is going to show up quite a bit because it is a common value for an angle. Okay. And again, this question doesn't specify height or time using H or T. We are welcome to stick with Y's and X's. We can kind of do whatever best suits our needs in the moment. Here I am going to stick with Y's and X's just because that's something that we are the most familiar with. But please know that you can make that change. And if something's predefined for you, we need to follow through with that. Okay. Whew. We should be able to get that equation, and hopefully you got something like I've got here, because we just have one final question. When Jamie is more than 9 meters above the ground, she could see the ocean. Wow. How long can Jamie see the ocean during her ride? So we know a couple of things that I want to point out. Thing number one, Jamie's riding the wheel for 5 minutes, which means she's making 2 full rotations. Because if one rotation only takes 2.5 minutes, then she could do 2 rotations in 5 minutes. Okay. When I take a look at this, I can use Desmos and plug in y is equal to 9. And I can figure out how long, or in each segment there, how long she's above that 9 meter mark, right? And I just take those 2 x values and I subtract them. Now, I have options. I can do that for both sets here. Subtract them to find the time within that first kind of cycle. Subtract to find the time within the second cycle, and I could add them together. Please know that when you do either of those subtractions, you will get the same exact number, because a sinusoidal graph has this repetitive pattern, which means it'll always give you that same answer no matter which one of those the wave patterns we're looking at. So what I'm going to do is I'm going to take a look at when I plug this in of y is equal to 9. I'm going to just look at that first bump, and that first bump gives me an x value of 0.881 and an x value of 1.619. And I'm going to subtract them, right? That's the time in the first rotation around the wheel that she's spending above 9 meters. So 1.619 minus 0.881 gives me 0.738 seconds. Now remember, that's the time in one rotation of the Ferris wheel that she's above the 9 meter mark. But Jamie doesn't go around once, she goes around twice. So my final answer is not this number. The answer is that final answer is that number times 2. So I'm going to take 0.738. I'm going to times it by 2, and that will be my final answer. I do have to round my final answer to 2 decimal places. And when I do that, I should get 1.48, and my units for time this time round are in minutes. Okay, that is it. That is the whole grade 12 applied course. You are done. We are done. We finished it all. Congratulations. I hope you have a really good rest of your day, and I hope you do the 9.5 practice. With all that being said, bye.